So, as you heard in previous talk, that gastrointestinal nematodes are a significant problem for livestock producers because of the damage they cause to the digestive tract of the livestock, causing significant weight loss and potentially causing fatal conditions for weakened animals. There are quite a few species of gastrointestinal nematodes that affect livestock, but the life cycles of most of these nematodes are quite similar. The adult stage is spent within the livestock animal itself, and the females produce eggs that are deposited in the intestinal tract, and they are eliminated from the animal with the dung. And those eggs will not hatch until they are in a high oxygen environment. So inside the gut, they don't hatch because the oxygen is virtually absent. And then once the feces are deposited, the oxygen level will increase, which causes the eggs to hatch. And then the nematodes will go through three larval stages within the dung. And the third larval stage is referred to as the infective stage. They keep their exuvium from the second larval stage, which provides a bit of protection. And those larvae, the third instars, will then migrate to vegetation and to soil. And it's when they're on the vegetation that they're then able to be reinfecting livestock, because when the animal is eating the vegetation, they pick up the L3 larvae, which then go through two more larval instars inside the gut and then eventually mature to the adult stage. And this diagram shows the life cycle for Himacus contortis, which you may have heard of as the barber's pole worm, which mostly affects sheep and goats. It can affect cattle as well. But the life cycle for something like Ostertargia ostertargi, the round stomach worm, which is a major pest of cattle, is virtually identical to this. So the L3 larvae are ingested at the top when an animal grazes on vegetation that's infected with the larvae. And then the larvae go through several more molts and then to the adult stage. And then the eggs are passed in the feces. And depending on the conditions, those eggs will hatch out and go through those three larval stages within a matter of days or weeks. And then they migrate to the vegetation, where they're then picked up by the adult and the life cycle continues. So this is the portion of the life cycle that's relevant to my study. That's what's going on in the dung. And we'll see where dung beetles figure into this as we go through this a little further. But I want to describe the Nem Toad model first, which is actually the easy part of this whole process. So it's known that the development of these larval stages of nematodes are influenced by temperature, of course, increasing with temperature and then eventually plateauing and then dropping off if the temperatures get too hot. Fecal moisture content also has an impact on egg hatch and the larvae, the mortality of larvae, and oxygen levels within the dung pad will affect the rate of egg hatching. And we've got some pretty good data on many of these environmental parameters and how they influence the development rate of the major pest nematodes, such as Himacus contortis and Ostertargia. And so we can get good life history parameters for those species and come up with a reasonable population model. And I used a distributed delay module to simulate the progress of the larvae through the larval stages, and then changing their development rate depending on the temperature within dung, the fecal moisture content, and the oxygen levels. We know the mortality is influenced by temperature and fecal moisture content, and that's easily incorporated into the model. And then finally, we have movement of the third instar larvae from the dung to the soil and vegetation. And that rate of movement depends on conditions within the dung and also outside the dung, especially things like free moisture. But there's some pretty good sources of data to model those processes. There's been some pretty good studies, a number of which were done in Australia, so they're very relevant to the conditions that we're trying to model here. The output of the model, okay, so the general model structure is, it looks like this, where we start with a clean pasture, and we add 1 dung pat per day, and we'll step through 365 days just as a starting point. We'll go through 1 year. And for each day, we'll read the climatic conditions. We've got some pretty good historic weather data that will be very useful for this. And then dung environmental conditions are calculated for each of the pats that are in the pasture. And then we progress the nematodes through their larval stages and hatch eggs according to environmental conditions. And then eventually migrate the third instar nematodes to the vegetation. And that will be the most important measure of the nematode population, is how many of the L3 larvae are available to be a source of reinfection for livestock. So that will be the major output variable, the number of L3 larvae on vegetation. And so this is just a sample output of what the model produces, using a simulated weather profile of just constantly fluctuating temperatures. And you can see that the number of L3 nematodes in the dung on the vegetation and in the soil fluctuate depending over time, and the number in the respective compartments here, vegetation, soil, and in the dung, will depend on migration rates that are easily manipulated in the model. And so this is a very straightforward process. However, it gets more complicated when we look at the impact of dung beetles on this whole situation. Dung beetles are known to impact gastrointestinal nematodes in dung in a couple of ways. First, we can get outright removal of the larvae and eggs from the population by burial of dung by the burying dung beetles. Whether or not those larvae can subsequently, nematode larvae can subsequently reemerge and reinfect larvae at a later date is a topic for another study, but that's something that we can't totally discount. Although I think in most conditions, at least in the more arid conditions of Australia, that avenue in reinfection is pretty minimal. However, there are some other things that dung beetles do to dung that impact the life history of nematodes. And the shredding of dung by dwelling and burying dung beetles will change the temperature of the dung, as well as the fecal moisture content very heavily, and oxygen levels within the dung. And it's the oxygen levels in the dung that are probably of greatest concern, because the oxygen is required for hatching of nematode eggs. So even though there are many documented benefits of dung beetles on the agroecosystems, there is a potential for a negative impact, and that is the increased hatching of nematode eggs in dung because of tunneling of endochropid and parachropid dung beetles in dung, and their effect on oxygen levels and subsequent hatch of nematodes. At the same time, that tunneling will result in decreased moisture content in the dung, which will have an adverse effect on the nematodes. And because of the dynamic interaction between the fecal moisture content and the oxygen levels, we can't really easily make predictions what the effect of dung beetles will be. And that's why a modeling approach was taken, to see how these parameters would be affected by dung beetles, and then how they would eventually affect the population of L3 nematodes able to reinfect livestock. So the main question is to be addressed by this model is, what is the impact of dung beetle activity on the population dynamics of the free living stages of gastrointestinal nematodes? This is just a simplistic view of the model. We have eggs that hatch and go to the first instar larvae, second instar, and third instar. And this is occurring within the shaded box indicating dung. And then the L3s leave the dung and go to vegetation. The rates at which these nematodes go from these different life stages is determined by characteristics within the dung, the temperature, fecal moisture content, and oxygen. The rate of migration to the vegetation is determined by fecal moisture content and rainfall. And then finally, we have mortality and dung burial, which will decrease the number of larvae and eggs from the population. So I realize that I'm getting close to end, but I'll just start. I just would like to just quickly describe the big challenge that I'm facing. And when I started off on this venture, I looked at a dung pat like this. It's just a wad of dung, but it's actually much more than that, because we have things occurring in the crust of the dung pat that occur at different rates than the interior portion of the dung pat. And so I've had to develop a dung submodel to track the conditions within these regions of the dung pat separately. So I've divided the dung pat into a crust and a core zone, and I'm looking at rate of temperature gain in the crust versus core, oxygen migration to the crust and core, both as a function of diffusion as well as facilitated by dung beetle tunneling activity, the effect of rainfall on the fecal moisture content, as well as loss of moisture from those regions by evaporation, and then the removal of dung from the pat by dung beetle activity. So these are all incorporated into the model. And so now the modified model is a bit more complex, mostly because we're tracking the populations of the nematodes in the crust and core zones for all of these dung pats separately. But the processes occurring for any one of these zones is the same. It's just much more complicated because we're looking at a number of pats. We have to look at the pats that are laid down each day, plus the different zones in each pat. And so the output of this model will then be the number of L3 nematodes on the vegetation. And the driving variables will be the degree of shredding, the timing of shredding, and the rate of dung removal by dung beetles. And there's impacts on the nematodes. I plan to use the model using weather data from different regions within Australia and New Zealand. And then possibly we could extend this to look at the effect of climate change, things such as the different temperatures and rainfall patterns on these life processes of the nematodes, the effect of variable stocking densities over time, and how that would affect nematodes on the vegetation. So that's the goal, and very soon we'll have some interesting data. We need to have good estimates of these effects on the dung, but that's my current challenge. So I think my time is up. So I thank you for your attention, and I am happy to conclude this symposium, and thank you for the invitation to participate. And acknowledgements also to the Dung Beetle Ecosystem Engineers program, which has made this work possible. Cheers.
Thank you very much, Paul. So as we all know, we've got half an hour open discussion, but we can start off with any questions to Paul. Just ask out loud or type in the chat box.
I have a question, which might not be a very smart question. We'll see. So what about bush flies? I'm wondering if, because, you know, they kind of are in the dung as well, they move a lot of the dung, and eventually they will use a lot of it. So would they actually have an impact on nematode as well?
Yeah, so you would expect, to the extent that they would be tunneling through the dung, they would be introducing oxygen into the interior of the dung pat. So I don't know how much tunneling they actually do, because I know that the eggs would be deposited on the dung pat and the larvae would develop within the pat. Do they do much in the way of tunnel creation? It seems to me they would, but I don't really know for sure. Anybody?
Yeah,
have
don't
any
spin it.
idea?
Yeah, actually, Pat might be able to answer that. But yeah, because sometimes we go in the field and you turn a pad, it's dry, but you turn it, then it's just all shredded, and it's actually from the flies. So initially, it's just kind of, I guess, very juicy, but then eventually it breaks down. So, but I don't spend enough time in the field either to know.
Yeah, no, that's a very interesting question, Val. It's definitely not a silly question. But I have no answer to that.
Paul, can you exit this share screen function,
Yep,
please?
there we go.
And we've been asked to turn on cameras when you ask questions out loud, please, everybody. And there is a question in the chat box. Does the success rate vary between species and egg? Sorry, that would
It's for Val.
that's to Val. Sorry, beg your pardon. I was going to ask Paul, are you thinking about adding anthelminthics to the model at some point?
That would be very easily done. It would mostly, if we have good data on the impact of the anthelminthics on the nematode population in dung, and the rate at which it would diminish in activity over time, it would just be a simple matter to add that into the mortality factor that's applied to each of the larval stages of the nematodes.
I was thinking it might be nice to do the targeted selective treatment approach that Megan talked about, where only a certain proportion are treated at any time.
Yeah.
Other questions for Paul before we open up to all of our participants? If there are no more direct questions to Paul and his nematode model, thank you very much, Paul.